Okay, think about this for a second. The single most extracted natural resource we have, it isn't oil. It's not gold. It's actually fresh water.
That's right.
And well, the rate we're seeing freshwater scarcity pop up globally is, frankly, quite alarming.
It really is.
So let's dive straight into why. Today, we're really digging into water scarcity, specifically within agriculture, based on some, well, pretty eye-opening research.
Yeah, and what just jumps out immediately from that research is just the sheer thirst of agriculture.
Right.
I mean, it's not a small amount. This sector uses nearly 70% of all the fresh water we take, from rivers, from groundwater, everything.
70%, wow.
And then you think, okay, our global population is growing by about 81 million people every single year. You add climate change, making things more unpredictable. Well, suddenly understanding agricultural water scarcity becomes incredibly urgent. You just see it.
Absolutely. So our mission here with this deep dive, it's pretty straightforward. We want to pull out the essential knowledge, the causes, the impacts, and maybe some potential ways forward for water scarcity in farming. We're focusing on what you listening right now need to know to really get a handle on this critical issue quickly, but, thoroughly.
Okay, so let's maybe lay some groundwork first. What do we actually mean when we say water scarcity?
Good point.
At its heart, it's a mismatch, basically. The demand for fresh water is just higher than what's actually available.
Right, more needed than we have.
Exactly, but it's a bit more complex than just numbers. It's also about whether people can actually get reliable access to water that's, affordable and safe to use.
Okay. So access is key too. And the research broke it down into two main types, didn't it? Physical and economic.
That's it. Physical water scarcity, sometimes called absolute scarcity. Well, that's when there literally isn't enough water in an area to meet everyone's needs.
Physically not there.
Physically not there. And about 1.2 billion people are living with that reality right now, often in drier parts of the world, as you'd expect. The key is demand just outstrips the natural supply.
Okay.
But it's not always like a constant year-round thing either. What's quite striking is that something like 67% of everyone on the planet experiences water scarcity for at least 1 month every year.
67%. So for a lot of people, it's seasonal.
It's very seasonal, and that's definitely being amplified by climate change, messing with rainfall, and of course, just more people needing water.
Right.
Now, when we talk specifically about water in agriculture, we really need to get our heads around the difference between blue water and green water.
Okay, blue and green water. Can you give us the quick breakdown on that?
Sure. So think of green water scarcity, GWS. That's what happens when there just isn't enough rainfall for crops to grow properly.
So not enough rain.
Not enough rain, which naturally means you need irrigation, right?
Yeah. Makes sense.
But here's a surprising thing. Green water actually supports about 65% of all the crops grown worldwide.
65% from rainwater.
Yeah. Yet, it hasn't really gotten the same attention in big global goals like the SDGs compared to other water issues, which seems like a bit of an oversight given how crucial it is.
That definitely puts it into perspective, yeah.
So that's green water. Then you've got blue water scarcity, or BWS.
Okay.
This happens in those same areas that might face green water scarcity, but the issue here is there isn't enough surface water, like rivers and lakes or groundwater that's our blue water, to irrigate the crops properly when the rain doesn't come.
So you need to irrigate because there's not enough rain, but then you don't have enough river or groundwater to irrigate.
Exactly, you've got it. And BWS, blue water scarcity, is increasingly seen as this major threat, not just to food, but also energy production. And it is actually a specific target in the UN's Sustainable Development Goal number 6.
Okay, so green is rain, blue is irrigation water from rivers and groundwater. Got it. But the research also mentioned agricultural economic water scarcity. AEWS. That sounds different again.
It is, yeah. AEWS is a situation where you've got croplands facing green water scarcity, so not enough rain.
Right.
But they aren't being irrigated even though there actually is enough blue water nearby to do it.
Wait, so the water's there, but they're not using it. Why?
Well, the reason isn't a physical lack of water. It's more about socioeconomic factors, maybe political barriers, things that prevent investment in irrigation or stop farmers accessing the water that's technically available.
So it's about infrastructure or policy or cost.
Exactly, things like that. And the researchers were pretty clear that we still need to learn a lot more about, how widespread AEWS is and what its full impact is globally. But the crucial thing here is that Fixing water scarcity isn't just about having enough H2O around, it's also about making sure people have fair access and the resources to use it.
That's a really key distinction. It's not just is there water, but can people get it to the fields? Okay, so now we understand these different flavors of scarcity. How widespread is the actual problem? What are the impacts we're seeing?
Well, the reach is pretty substantial. And like we said, it really varies depending on where you are and what time of year it is.
Right, the seasonal aspect.
Yeah. So green water scarcity, that affects a massive 76% of the world's croplands for at least 1 month a year.
3/4 of all croplands.
And about 42% of those areas deal with it for 5 months every year.
Wow.
Currently, the estimate is we're using about 5,406 cubic kilometers of green water on crops annually.
Which is hard to picture. How much is that?
Well, 1 cubic kilometer is like 400,000 Olympic swimming pools. So multiply that by over 5,000. It's a huge volume.
Yeah, that is immense.
It really is.
Yeah.
And if we just tried to make up for that lack of rainfall purely with irrigation without even thinking about whether our rivers and groundwater can sustain it, we'd need an extra 2,860 cubic kilometers of blue water every year.
Just staggering numbers.
They are. Now, if we look at blue water scarcity, the picture is also concerning. Many areas that rely heavily on irrigation are already feeling the strain. About 68% of irrigated croplands face blue water scarcity for at least 1 month a year.
Okay.
And 37% deal with it for 5 months.
And we're not just talking small plots here. These are major food baskets, right?
Absolutely. Think about places like the U.S. High Plains or California's Central Valley, Mexico, Spain, North China, the Murray-Darling Basin in Australia.
Okay, Pakistan.
Exactly. Vital agricultural lands in India and Pakistan, too. These are all heavily irrigated regions that experience significant blue water scarcity for big chunks of the year. And that has major implications for, global food security.
It really paints a worrying picture for where a lot of our food comes from. What about that third type, agricultural economic water scarcity, AEWS? How big a deal is that?
So AEWS affects about 15% of global croplands. That's roughly 0.14 billion hectares. What's also quite worrying is that about 16% of the land we currently farm is being irrigated in ways that just aren't sustainable in the long run. And in these AEWS regions, farming often relies completely on a single rainy season. So they're particularly vulnerable when water is short. The research found about 43% of AEWS croplands face scarcity for 1 month during their crucial rainy season. But a huge 86% experience it for 3 months.
86% for 3 months. And where are these AEWS areas mostly found?
Well, the research shows it's heavily concentrated in lower-income countries, often places that already have big gaps between how much food they could be producing and what they actually are.
Why there specifically?
It seems largely due to a lack of investment in the irrigation infrastructure they'd need to actually use the blue water that might be available. In wealthier, drier regions, developing irrigation tends to be a much higher priority to boost food output.
Right, they invest more readily.
Exactly. Geographically, about 2/3 of these AEWS croplands are in sub-Saharan Africa, Eastern Europe, and Central Asia.
So it's often hitting countries already facing big economic challenges.
That's a really crucial point, yeah. It tends to worsen existing inequalities.
And this isn't just about surface water like rivers, is it? The research mentioned groundwater depletion, too.
Oh, absolutely. Overusing groundwater is a massive global issue. It's estimated to affect about 1/3 of the planet's largest underground reservoirs, aquifers they're called.
Right.
When we pump water out faster than rain can naturally refill it, we're essentially, draining a savings account. It's a finite resource we're drawing down, and that has really serious long-term consequences for water availability.
All of this. It sounds like it could lead to problems way beyond just farming output. You mentioned potential conflicts, people having to move.
That's a very real concern, yes. As water gets scarcer, competition just heats up.
Yeah.
And that puts immense pressure on governments, right? How do you allocate this vital resource? Farming, industries, cities, the environment.
Tough choices.
Inevitably, some groups might get access while others miss out. And yes, chronic water scarcity can definitely be a driver for migration, both within countries and across borders. And in some situations, sadly, it can even fuel conflict, especially in regions that are already, politically fragile. It's pretty sobering to think that back in 2017, the World Economic Forum ranked water crises as the 3rd biggest global risk.
3rd. What was ahead of it?
Weapons of mass destruction and extreme weather events.
Wow. Okay. That really puts it into perspective.
Yeah.
And the impacts aren't just social or political, are they? They ripple through the environment, the economy.
Precisely. They're all deeply interconnected. Socially, well, lack of access to clean fresh water forces people to drink unsafe water. That leads to diseases like typhoid, cholera, horrible stuff.
Yeah.
Even big projects meant to help, like dams for water storage, can sometimes end up causing conflict over water rights between different areas or communities. And interestingly, sometimes having a big reservoir can make communities feel secure, but maybe less prepared for future droughts. They sort of relax a bit.
That sense of security paradoxically leading to less preparation. Okay. What about the economic side?
Economically, well, countries facing scarcity might have to spend a fortune importing water or building incredibly expensive supply systems.
Right.
The actual cost of water can go up, hitting businesses, hitting consumers. And crucially for our topic today, if there isn't enough water for irrigation, crop yields plummet. That can devastate economies that really depend heavily on agriculture for jobs and income.
And the environmental cost. What does that look like?
Also severe. We see natural habitats destroyed, biodiversity declining. Overpumping groundwater, like we mentioned, can actually cause the land itself to sink. It's called land subsidence.
Really? Land sinks.
Yeah. And treating water to make it safe often needs a lot of energy. If that energy comes from fossil fuels, well, that adds to climate change, which then makes water scarcity worse. It's a real vicious cycle.
It really is. Okay, so given all these intertwined challenges, what can we actually do? What are some of the solutions being looked at for agriculture? The research stressed needing a broad approach, right?
Yes, definitely. A comprehensive strategy is vital. You have to consider the economics, the environment, and, social equity, the triple bottom line, they call it.
Right.
So some key areas. Public education and good policies are just fundamental. You need people aware and conserving, and you need rules for sustainable management.
Makes sense.
Protecting and restoring ecosystems is also really important. Think wetlands, forests, they act like natural sponges, collecting water, filtering it, storing it.
Nature's infrastructure.
Exactly. And then incentivizing farmers to use sustainable methods helps protect water sources from pollution, like fertilizer runoff.
What about financial levers like taxes?
Yeah, that came up. Using water taxes for big industrial or agricultural users could discourage waste, ideally without hitting household tap water prices too hard. There's also the idea of somehow taxing or penalizing major food waste generators.
Okay, food waste. That seemed like a really big piece of this. The numbers were pretty shocking.
It's a huge piece of the puzzle, yeah. The research suggests that if we could have global food loss and waste,
Just have it.
that alone could cut the water footprint of food production by maybe 12 or 13% and potentially ease water scarcity for over 720 million people.
That's incredible.
It is. We lose something like 1.2 billion tons of food just on farms every year.
On the farm itself,
Absolutely.
before it even leaves.
Yeah. And then another 30 to 40% gets wasted further down the supply chain.
Wow.
So educating farmers on better storage, better handling, and educating consumers about reducing waste at home. It's all crucial. Though honestly, the research noted there isn't much hard evidence yet that government incentives for cutting household food waste are really working on a large scale.
Interesting. Needs more effective approaches there, maybe. So it's not just growing smarter, but using what we grow much better. What about tech and infrastructure? Irrigation came up a lot.
Absolutely. Improving irrigation technology is critical. Things like setting clear targets for reducing water use in irrigation, funding more efficient systems like drip irrigation, that's essential.
Right.
And just basic stuff like fixing leaky pipes and canals in existing water infrastructure, that can save a lot of water.
Yeah, the basics matter.
They really do. And sustainable irrigation, done right, doesn't just save water. It helps produce more food and makes farms more resilient to climate change impacts.
But current irrigation is often not sustainable.
Unfortunately, a lot of current irrigation is estimated to be pushing past the safe planetary boundaries for water use. But the potential upside is huge. If we could implement sustainable irrigation in those AWS regions we talked about.
The ones with water available but no infrastructure.
Exactly.
Yeah.
That could significantly boost global calorie production.
Okay. And then there was this idea of net regenerative agriculture. That sounded potentially transformative.
It really does have significant potential. Regenerative agriculture is all about building healthier soil.
Healthier soil holds more water.
Precisely. Healthier soil acts more like a sponge, holding more moisture, which reduces the need for irrigation and minimizes water running off the surface.
Wow.
It also improves fertility and lets water soak in better.
How does it work? What do farmers do?
There are sort of 5 main principles usually mentioned, things like disturbing the soil as little as possible, so less plowing or no-till farming,
Okay.
keeping the soil covered with plants like cover crops, maximizing biodiversity, different plants, maybe increasing animals, minimizing chemical inputs, and really adapting practices to the local environment.
So it's whole system approach.
It's a whole system, yeah. It's still evolving, and it probably needs new economic models and policy support to really take off widely. But it's a very promising direction for more sustainable water use.
What about reusing water? Treated wastewater came up.
Yes, definitely.
Right.
Especially in places with severe water shortages and lots of people, reusing treated wastewater can be really effective.
Yeah.
Well, it directly reduces the demand on freshwater sources, obviously, but it can also help improve the health of rivers and lakes by reducing the amount of polluted water being discharged into them.
And you can use it for irrigation.
Absolutely. It fits really well into a more circular economy approach, using waste as a resource. Technologies like constructed wetlands are a good example of a cleaner, more nature-based way to treat wastewater for reuse.
Okay. And for those really dry, arid regions, desalination seems like an option, though maybe a tough one.
It is vital in many arid regions, yeah. Places like Saudi Arabia rely heavily on it. Desalination turns seawater into usable freshwater.
But it uses a lot of energy, right? And it's expensive.
That's been the main drawback. High energy consumption, often from fossil fuels, which means high costs and environmental impact. But technology is improving. Things like solar-powered reverse osmosis are making it more sustainable.
Solar-powered.
And there's even research into recovering valuable minerals from the salty brine that's left over after desalination. That could potentially offset costs and reduce the environmental headache of disposing of the brine.
Turning waste into a resource again.
Exactly. But still, desalination is generally seen as, a last resort when other freshwater sources just aren't economically viable.
Got it. The research also mentioned a couple of other, maybe less common ideas. Agriculturally managed aquifer recharging, Agimar, and rainwater harvesting.
Yeah, Agimar is basically about using farmland intentionally to help surplus surface water, like floodwater, soak down into the ground and recharge underground aquifers.
Using farms as recharge basins.
Kind of, yeah. Given how much land is used for farming, the potential recharge volume could be significant, but there are still questions.
Like what?
Well, how does it affect crop yields? Could pollutants from the farm leach into the groundwater? What about waterlogging fields? Does it take too much water away from rivers downstream? Is it economical? Are there policy hurdles? Where's the best place to do it? Does it release greenhouse gases from the soil? Lots to figure out.
So, promising, but needs more research.
Definitely needs more R&D. And rainwater harvesting, just collecting rainwater, usually for non-drinking uses like gardening or flushing toilets that's more decentralized. It can reduce demand on the main water supply and help manage stormwater, especially in cities.
But it's not always reliable.
Well, it depends entirely on rainfall, so supply can be inconsistent. And sometimes, setting up individual systems can actually be more expensive than relying on the centralized water grid. So its feasibility is sometimes debated.
It really sounds like there's no single silver bullet here. It's going to take a mix of all these different strategies.
That's absolutely the takeaway. A combination is needed.
Now, the research also spent quite a bit of time on something called water footprint analysis. What exactly is that, and how does it help with managing water scarcity in agriculture?
Right. The water footprint, or WF, it's essentially a tool, an analytical method that lets us quantify the total amount of water used and the level of water pollution involved in producing pretty much anything, goods, services, including everything that goes into agriculture.
So it's like a full accounting of water use.
Exactly. It helps us understand the true water cost of what we make and consume, which is obviously crucial if we want to move towards more sustainable practices. The EU has its Water Framework Directive aiming to improve water quality and availability. WF analysis provides the kind of data needed to support goals like that. It's designed to be a comprehensive indicator. It looks not just at how much water, but also where and when it's used. It gives you the whole picture.
So it's not just the water poured onto the crops themselves. It includes water used to make fertilizer or build the tractor.
Precisely. It tries to capture all of it. The framework for doing this is called Water Footprint Assessment, or WFA. It usually involves 4 steps.
Okay.
First, you define your goals and scope. What are you measuring and why? Second is the accounting, calculating the footprint itself. Third is assessing sustainability. Is this level of water use okay? And fourth is figuring out responses, what can be done to improve things.
And the accounting part breaks the water down. You mentioned blue and green water before.
Right. The accounting breaks it into three components: the blue water footprint, the green water footprint, and the gray water footprint.
Okay, we covered blue, surface groundwater for irrigation, and green, rainwater used by crops. What's the gray water footprint?
The gray water footprint is basically an estimate of how much fresh water you'd need to dilute pollutants from a process back down to acceptable water quality standards.
Ah, so pollution dilution water.
Exactly. So, for example, the runoff of excess nitrogen fertilizer from a farm. The gray water footprint is the volume of water needed to dilute that nitrogen down to safe levels in the receiving river or lake.
Got it. So total footprint equal blue plus green plus gray.
That's the idea. And there's also this related concept of virtual water.
Virtual water.
Yeah, it's the water that's kind of embedded in traded goods. When a country exports grain, it's also exporting all the water that was used to grow that grain.
So like indirect water trade.
Precisely. And farmers, of course, are in a really key position because their choices directly influence all three components: blue, green, and gray footprints.
Through irrigation choices, soil management, fertilizer use.
Exactly. Which is why, again, educating farmers on these more holistic, regenerative, water-efficient approaches is so critical. Now, there is a bit of an ongoing debate in the field about whether the water footprint should primarily just measure the volume of water used, or if it should focus more on the actual environmental impact of that water use.
Volume versus impact.
Right. Both perspectives offer useful insights, really.
And there are different specific methods for calculating the footprint.
Yes, broadly two main approaches. There's the volumetric approach, largely based on Professor Arjun Hoekstra's work at the Water Footprint Network, that really focuses on mapping and summing up all the direct and indirect water volumes along a product's supply chain.
Okay.
Then there's the impact-based approach, which is more aligned with the ISO standard 10046. That tries to assess the cause and effect links between water consumption and its consequences for human health, ecosystems, resource depletion, and so on.
So more focus on the consequences.
Exactly. And because the ISO standard itself doesn't prescribe one single way to assess those impacts, various specific methods have been developed under that umbrella.
The research mentioned a water scarcity index, WSI, and specific methods in software like SimaPro.
Correct. The WSI is often used as a kind of midpoint indicator, a way to gauge how stressed water resources are in a region. And yes, life cycle assessment software like SimaPro incorporates different methods for calculating WSI. The paper mentioned methods by Boulay and colleagues, Berger et al., Hoekstra et al., among others.
Do they measure different things?
They use slightly different formulas and focus points. For example, Boulay's method looks at a consumption to availability ratio and, importantly, tries to model the consequences. Berger's looks more at the vulnerability of river basins to depletion. Hoekstra's also uses a consumption to availability ratio. Interestingly, the Boulay method is the only one of those mentioned that explicitly tries to extend the assessment to endpoint impacts, specifically potential effects on human health.
Okay. So different ways to slice the data.
Pretty much. And the general consensus among experts seems to be that using a range of these WF assessment methods is probably the best approach. It gives you a more robust, comprehensive picture. And that helps water planners make better decisions, set priorities, and develop more effective sustainability strategies.
This has been incredibly insightful, a really comprehensive overview. So just to try and bring it all together, what are the absolute key things we should take away from this deep dive on water scarcity in agriculture?
I think the main takeaways are, first, that water scarcity in agriculture is a really complex and, frankly, growing global challenge. It has these significant knock-on effects, environmentally, economically, socially, and it's being driven largely by population growth and the impacts of climate change.
Okay. And understanding the different types of scarcity is important.
Absolutely crucial. Getting the difference between physical and economic scarcity and between blue and green water scarcity is key to understanding the problem properly.
And as we discussed, there's no single magic fix.
No, definitely not. It's going to require a whole toolkit of interconnected solutions, everything from raising public awareness and adopting sustainable farming like regenerative ag, all the way to advanced tech like wastewater reuse and maybe desalination in some places.
Right, a whole spectrum of actions.
Yeah. And underpinning a lot of the management side is using tools like water footprint analysis to actually measure, understand, and then hopefully reduce our water consumption effectively, especially in agriculture.
Okay. So as we think about this, the fact that fresh water is finite and it's absolutely essential for growing our food, here's maybe a final thought for you, our listener, to chew on. Thinking about your own life, what personal changes or maybe areas you want to learn more about, what resonates most with you when it comes to contributing to a more water-secure future? Perhaps it's looking into your own water footprint, or maybe just being more conscious of the water embedded in the food choices you make every day.
Yeah, it's a really important point. Ultimately, tackling water scarcity needs everyone pulling together. It's individuals, it's communities, it's policymakers, it's researchers, all working towards those shared goals of, sustainability and making sure there's enough clean water for everyone now and in the future.